All right, in this video, we are going to talk about problem 7.76 from our textbook on early onset dementia. It says dementia is the loss of intellectual and social abilities severe enough to interfere with judgment, behavior, and daily functioning. Alzheimer's disease is the most common type of dementia. In the article Living with Early Onset Dementia, exploring the experience and developing evidence based guidelines for practice, P. Harris and J. Cady explored the experience and struggles of people diagnosed with dementia and their families. If the mean age at diagnosis of all people with early onset dementia is 55 years, find the probability that a random sample of 21 such people will have a mean age at diagnosis less than 52.5 years. Assume the population standard deviation is 6.8 years. State any assumptions that you make in solving this problem. Okay, so let me write all that down. All right, so 7.76. Okay, and the mean age at diagnosis is 55. Simple random sample of size 21. So n is 21. Assume that the population standard deviation is 6.8 years. So sigma is 6.8. All right, and then what is it that we want to do? We want to find the probability that a random sample of 21 such people will have a mean age less than 52.5. So we want to find the probability that x bar, the sample mean, is less than 52.5. Okay, so here's all the information, and I wrote it right in the middle again. Okay, what we need to do, right, to calculate this probability, it involves the sample mean, right? So we know that we are going to use the sampling distribution of the sample mean. All right, so we have to figure that out first. So what is the mean of the sample means? We know that that is the same as the population mean, so 55, right? What is the standard deviation of the sample means? Well, we know that is the population standard deviation, 6.8, divided by the square root of the sample size. Okay, and so we will go and calculate that out. Let's see, what do we get here? We get 6.8 divided by the square root of 21. That comes out to be 1.48 4 to 3 decimal places. 1.484. Okay. All right, and so now what we need to do is, now that we have that sampling distribution of the sample mean, we can calculate this probability. So I'm going to draw what that looks like. Okay, so we know that the mean is right here at the hump at 55. So 52.5 would be less over here. And we know that we want the area there to the left, right there. Okay. All right. So to calculate that area under the normal curve, we're going to calculate the z-score, right, of 52.5. Using the sampling distribution of the sample mean. All right, so it's going to be 52.5 minus 55 all over 1.484. And let's calculate that out. So it is 52.5 minus 55 divided by 1.484. So that comes out to be minus 1.68 to 2 decimal places. Okay. All right, and so now we would go look up minus 1.68 in table 2. So minus 1.6 is right here. And then 8. Right here. 0.0465. All right. And here, because we want the area to the left of 52.5, we don't have to do any calculations at all, because that's exactly how table 2 kicks out its answer. So the answer here is 0.0465. Okay. And then the last bit about calculating are what assumptions did we make here? We did make the assumption that that this distribution is approximately normal, right? Because the sample size, at the very least, approximately normal. The sample size, being 21 is lower than 30, right? So the central limit theorem really would not kick into place there. So we did make that assumption. On the tests and whatnot, I am not going to, I'm not going to make you make it so that it's not where you can't use this technique. But in reality, right, if you were doing some statistical analysis, then you'd have to be really careful about that. Okay, if your sample size was this low and you didn't have some good evidence that this distribution was at least approximately normal. Okay. All right, and that's it for this problem.